here, chapter 20, which is the chapter that comes after 19, the chapter that comes before chapter 21. This is PN junction diodes, and I get emotional because this is your first real component, solid state component, that is. It's your first real electronic component, because when you figure everything you've studied up to this point, capacitors, inductors, are they truly electronic, or are they electrical? But this is truly electronic, because this is made of solid state stuff. After completing this chapter, you're going to be able to describe what a junction diode is and how it's made. Define the term depletion region and barrier voltage. Explain the difference between forward bias and reverse bias of a diode. Draw and label the schematic symbol for a diode. Describe 3 diode construction techniques. Identify the most common diode packages. Test diodes using an ohm meter. Now, PN junctions. PN junctions. Mobile charges. Remember how electrons and holes that drift? From last chapter, those are considered our mobile charges. Positive ions, an atom that has more protons than electrons. Negative ions are an atom that has more electrons than protons. Remembering that again, in the beginning, everything was in a neutral, natural state. When we apply energy to matter, we ionize it. Now, there are always an equal number of mobile and ionic charges within N-type and P-type semiconductor materials. Diodes are created by joining N and P-type materials together. When these materials come in contact with each other, they form a junction called a junction diode. This is what it would kind of sort of look like if you were an artist trying to depict it. You've got N material butted right up against P material, P and N material. We're going to create what's known as a depletion region. The depletion region is near the junction where electrons and holes are depleted and extends only a short distance on either side of the junction. So what's going to happen here is, remember these electrons of the N material, free electrons, where are free electrons going to want to go? To the P material to try to fill the holes. But can they fill the holes? Not necessarily. Here we've got P material, holes, where are the holes going to migrate? To the N. Why? They want to be filled by electrons. So this is going to create this depletion region, we call it. Sounds like something out of some sci-fi movie. Do not enter the depletion region. Also associated with the depletion region is what's going to be called the barrier voltage. Again, sounds like something out of a sci-fi thriller. The barrier voltage, we have opposite charges that build up on either side of the junction. This is because of those mobile charges. It can be represented as an external voltage source. Now, when I say it can be represented as an external voltage source, don't try to get a voltmeter, and measure the voltage of a diode. You can't measure this voltage. This is a barrier voltage. This is a voltage that must be overcome before you could get current to flow through this device. You get it? That's why it's called barrier voltage. Here's a new term for you. It's called bias voltage. Bias means operating point. So operating point voltage. When a voltage is applied to a diode, it is referred to as a bias voltage. Now in this particular case, what we see here is our voltage source with a negative on the right. Current flows negative to positive. So current is going to want to flow at an N material through to the P material and then complete the circuit path. This is a series circuit right here, is it not? When we put a negative on the N material and a positive on the P material, we are going to do what is known as forward biasing the diode. Forward biasing the diode. That's why this is a new symbol I'm going to introduce to you, I sub F, current forward. I sub F, current forward. When we do this, when we apply forward bias to a diode, this is where the diode kind of does its magic. For those of you that come from a mechanical background, some of you may be familiar with what's known as a one-way check valve. A one-way check valve would be, envision a straw, if you will, with a little ball sitting on top of the straw. As long as you're blowing through the straw, that ball is going to become unseated and air will be allowed to pass. But as soon as you suck on the straw, what's going to happen to the ball? It's going to seal it. So that will only allow the air to flow one way, but it won't be able to allow the air to flow the other way. It's a check valve, what's commonly known as a check valve. A diode is the electrical equivalent of a check valve. It's going to allow current to flow in this direction and this direction only. So when we forward bias a diode, current flows through it. Now forward bias, when the current flows from an N-type to a P-type material, the diode's forward bias. Germanium diodes require a minimum bias flow of, this is a typo, this should be 0.3 volts, not 0.03 volts. What I'm talking about is 300 millivolts, or 0.3. This is actually an approximation, so it might be a little less than that. This is not gospel. Don't get in a circuit and say, wow, Joe Grenick over at their technical college, or actually we just found out yesterday they changed the name. They're going to change the name of this place. Did you hear about that? It's going to be Technical Institute. Got that going for us. Maybe I'll get a new, different colored lab coat. So for germanium, it's going to be 0.3 volts. For silicon, it's going to be 0.7 volts. Approximation. And to be honest with you, that approximation could be anywhere 0.2, 0.3 volts for germanium, 0.6, 0.7 volts for silicon. What's that? Yeah, some of it's the manufacturing, the design, what specifically the diode was designed to do. So there's going to be some variance in that number. So that's why we say this is just an approximation. So if you know the 0.7 and the 0.3 for this class, you'll pass okay. When you get to the world of reality in the lab, all bets are off. You'll be close to these, but it won't be exactly. Don't come banging on my door if you don't get 0.7 volts. Well, Joe, you said in class. No, I didn't say in class. It's going to be exactly 0.7. The forward voltage drop. Once a diode starts conducting, a voltage drop known as a forward voltage drop occurs. Again, for germanium, it should be 0.3 volts. For silicon, 0.7 volts. that means that voltage drop, it's kind of the voltage that is going to be the price of doing business with a diode. Follow what I'm saying? You're always going to get that voltage drop across the diode when you forward bias it, because that's what I'm talking about right now. You know what I'm talking about, all right? What's up, Mr. Graham? It still is. It still is. That's why these components are going to get hot. Yep, and there's going to be a maximum amount of power that can be dissipated. That's why you raise a really good question. Basically, he or she who has the largest diode, physically the largest diode, wins, has the highest power. Because all diodes, a little tiny diode a silicon diode is going to drop 0.7 volts across it. A really big, huge diode is going to drop 0.7 volts across it. What's the difference between the two? The amount of power they can handle. Yep. And you could always, generally speaking, go bigger, but you can't go smaller. So if you've got a big diode that explodes and you're going to replace it, you need to replace it with a diode that is at least as equal to the original size or larger physically. If you go smaller, the smaller one will probably explode rapidly. Next thing we're going to talk about is reverse bias. Again, the magic of a diode. When you reverse bias a diode, the terminals are going to be reversed, meaning we're going to put a positive on the N material and a negative on the P material. When we do so, what's going to happen is we end up where the diode will not conduct because we build a larger, what did we call this? Remember from the sci-fi thriller? Do not enter the depletion zone, the depletion region. So when we reverse bias the diode, we physically increase the depletion region. So there's no way an electron trying to complete this circuit path is going to be able to make it through the depletion region. So therefore, the diode will be shut off. In this condition, I sub R, current reverse, it's going to act like an open. It's going to act like an open. There is going to be a small amount of a current that flows, and what we're going to call that is leakage current, but it's going to be really, really, really small. You'll also see a little bit of current flowing because what are we doing here? What's happening to the size of the depletion region? It's getting bigger. So if it's getting bigger, how could it be possibly getting bigger? Something must be flowing. And if something's flowing at any part in this circuit, it's going to be flowing in every other part of the circuit because it is a, what kind of circuit? Series circuit. Very good. And remember, the law with a series circuit, whatever happens in one part, current's constant. All that stuff that you learned about last quarter is really dependent. You understand it now. Diode characteristics, they can be damaged by excessive heat. They can be damaged by excessive reverse voltage. Let me go back a slide real quick. Talk about that reverse voltage. Let's say that this is like a little power supply. It goes 0 to 12 volts. And let's say I go 0 to 12 volts, and at 0 volts, obviously I have just the standard barrier voltage to overcome. As soon as I exceed 0.7 volts, or excuse me, as soon as I reverse bias it, what's going to happen is this depletion region is going to get bigger, bigger, bigger. I jack it all the way up to 12 volts, no problemo. I connect it to a now I crank it all the way up to 75 volts. Well, this diode, let's say, is only rated to go as high as 35 volts, reverse voltage. So as soon as I get up to 35 volts, this depletion region gets so freaking big that current is just going to arc through it, and it will destroy the diode. So all diodes are not created equally. You're going to have to look at the data sheet to see specifically how much reverse voltage this can handle. And they put a number on it. It's just as good. They put a 1N number on it. It's going to be 1N and then 4 other digits typically. And you could look that up on Google, give you the data sheet. And then you know exactly how much reverse voltage that is designed to handle. Now, at room temperature, reverse current is going to be very, very small. Room temperature, diode sitting there on the table. And obviously, as we know, as temperature increases, the resistance of the component decreases, therefore allowing more current to flow through it. So engineers really got to take this into consideration when they're putting something together. This is one of the things now that all of you will be held accountable to with your projects. Right? You build an electronic project and you think you're going to put a bunch of diodes or solid-state devices inside a sealed box and expect them to do wonderful things with high power. Well, unless you provide adequate coolant and cooling and airflow, heat's going to build up, and eventually it's going to explode and fail catastrophically. Question, Mr. Graham? Yep. Did that explode? So you know what I'm talking about. Yep. Down at the bottom is the schematic symbol for a diode. A diode has 2 terminals on it. The cathode and the anode. The way I always remember this is anode starts with the letter A, so does the word arrow. So arrow, anode. Arrow, anode. Cathode, well, that'd be the other side. Now, who do you think came up with the schematic symbol for a diode? Technicians, engineers, scientists that discovered it. Why? Who discovered it? Scientists. So who got to draw the schematic symbol for it? Scientists. Scientists didn't develop it, and they called a bunch of technicians and, hey, what do you think we should use the schematic symbol? No, scientists came up with this, and So I'm going to tell you something. Since scientists did this, scientists and engineers basically embrace whole flow. Scientists and engineers think holes flow from positive to negative, and that's current flow. You're all technical school students. Technical schools, 2-year schools, a lot of 4-year schools, the military, all embrace electron flow. So when you look at the schematic symbol and you see the arrow pointing from left to right, that tells you that holes flow from left to right when this device is turned on. So if holes are flowing left to right, which direction must current be flowing in? Electron flow. Right to left. In order for you to make current flow right to left, what polarity do I need to put on my cathode to turn this device on? What polarity do I need to put on my anode to turn this device on? I need to put a negative on the cathode and a positive on the anode. That way current will flow against the arrow. Electron flow against the arrow. Does that make sense? Electron flow will always be opposite the direction of the arrow. So here, as technicians, we study the behavior of electron flow. So when you're troubleshooting this, you put your black lead on the cathode, you put your red lead on the anode, and you would expect to see that forward bias voltage. Mr. Graham? Yeah, I believe that's what it goes back to. And again, we're technicians. We're technicians. And a lot of engineers, too, embrace electron flow. So I don't want you to lose sleep over electron flow. Like I said earlier in our last lecture, right? If 6.24 times 10 to the 18th electrons go that way per second, it's an amp. If 6.24 times 10 to the 18th holes go that way, and actually if 6.24 times 10 to the 18th holes are moving that way, what must be moving the other way? Because everything in the beginning was in a neutral natural state. So if I got holes going one way, electrons must be going the other way. So early on in my career, I lost a lot of sleep over that. Is it the holes that are moving or the electrons? And I just, for weeks, with headaches and migraines trying to think it doesn't matter. It really doesn't. But I want you to understand that whenever you see a semiconductor schematic symbol from this point forward and you see an arrow, the current we're talking about, electron flow, always flows against or opposite the arrow. Knowing that, let's talk about some circuits now. I'm going to ask you some questions. This right here is a 10-volt DC power supply. It's connected to the circuit right here. This is a silicon diode. What voltage will be present across this resistor? 9.3? How in the heck did you come up with that? Across where? Absolutely. Very good. Very good. It's a simple series circuit. Another term for a series circuit is a voltage divider. So we know the big thing you got to look at is we got the negative connected to the cathode, we got the positive connected to the anode, so that we know we're doing what to this? Forward biasing this. I kind of gave you a hint by showing the I sub F right here, forward bias. So current's going to flow through, create a 0.7 volt voltage drop here. So 10 volts minus 0.7 gives us 9.3 across that resistor. Make sense? If I pull this diode out and replace it with a germanium diode, what voltage will be present across the diode? 0.3, 0.2, 0.3, very good. The remainder voltage will be dropped where? Across the resistor. Okay, let's take a look at this bottom circuit. This right here is a silicon diode. What voltage drop will I get across this resistor in this condition? This is 12 volts applied. So what voltage am I going to have across this? What's that? 0. Very good. What voltage will I get across my diode? What's that? 12 volts. Why? You will always read source voltage across an open. When this is reverse bias, this diode is going to act like an open. So I got 12 volts minus 12 volts gives me a remainder of 0 volts. When this is reverse, let's look at it another way. When I'm reverse bias this diode, is there any current flowing in the circuit? How much current? When this is reverse biased, is there current flowing in this circuit? How much current? Just a little bit of current. What kind of current? Reverse current, leakage current. So realistically, is there really any current flowing in the circuit when it's reverse biased? No, that's why it's reverse biased. We're using the diode to prevent current from flowing in the circuit. That's why we put a diode in it. Make sense? So if I've got no current flow through the resistor, is it going to create a voltage drop? No. You need current flow through resistance to create a voltage drop. So other than a small amount of leakage current, if we have a small amount of leakage current, are we really going to get maybe a little small voltage across this? Yeah, but it's going to be insignificant. If you got in there with your meter, your multimeter, and you measure across here, you're going to get 12 volts. You measure across here, you're going to get 12 volts. You measure across here, you're going to get 0 volts, or some minuscule amount. Make sense? Diode construction techniques. We make these things 3 different ways, one of 3 different ways. We use a growth or a grown junction, an alloyed junction, or a diffused junction. Grown junctions are made with intrinsic semiconductor material, that's pure semiconductor material, and P-type impurities are melted into a quartz container. A semiconductor crystal called a seed, which is a perfect P-type crystal, is lowered into the mixture and rotated and slowly withdrawn, allowing the molten mixture to cling to it. The molten mixture cools and rehardens, assuming the same characteristics as the seed. As the seed is withdrawn, it's alternately doped with N and P-type materials. Back and forth. Almost like, again, if you've seen like the way the old-timers used to make candles. You get a wick, you dip it in the wax, then you dip it again, except what they're doing here is like dip it in one colored wax, dip it in another colored wax, one colored wax, another colored wax. But here we're using semiconductor material. The resulting crystal is then going to be sliced into many PN sections. That PN section where it's grown together is going to be a diode. It's that simple. Alloyed junctions, a small pellet or trivalent material is placed on an N-type semiconductor crystal. The two are heated until the pellet melts and partially fuses with the crystal. The area where the two materials combine forms the N-type material. The material is going to recrystallize, forming a solid PN junction. They might want to use this process here for maybe some higher power ones, because you want more physical material, so you could have a diode that's physically bigger, can handle more power. The diffused junction is the most popular method used today in the manufacturing of these. And if I could explain to you very briefly what diffusion is, if I had a glass of water and I put a drop of red food coloring in it, what would happen to that drop of red food coloring? It would be diffused into the water. So that concentrated form would be diffused into the water. The same process is used with these semiconductor materials. They place a mask with openings on a thin section of N or P-type semiconductor material called a wafer. We place the wafer in an oven and expose it to an impurity in a gaseous state. The impure atoms penetrate through the exposed surface of the wafer at extremely high temperatures. The length of diffusion is going to be controlled by the length of the exposure and temperature. So time and temperature is going to control how much diffuses into the material. And again, if you want to make a more stout diode, if you will, you'll leave it in there longer and diffuse it into the substrate longer. These are examples of diode packages. The diode must be packaged to protect it from both environmental and mechanical stresses. The two on the left are basically small through-hole components. The one on the right is considered a stud mount. It's actually considered what's known as a DO4, but this is big. This is a stud, right? This could take up to this could be a 1/4 inch thread on it, 1/2 inch thread. I mean, these things get big. Some of these get really, really big for high power applications. One of the things I want to point out with these on the left, you see this little black line? Or this side being dark, that's going to signify the cathode. For these stud mount packages, the physical package itself, excuse me, the physical package itself is going to be the cathode. So be careful if this is energized, if you're working on energized equipment, that you don't necessarily touch this outer case. It could be at a different electrical potential. The physical case is the cathode. Testing PN junction diodes, real easy. Check the forward to reverse resistance ratio with an ohm meter. One of the things I want to point out to you is when I say ohm meter, I am talking about an old school analog ohm meter. That's what I'm talking about. In doing your lab experiments associated with ELEC 120, we've got a couple analog meters in the lab. If you need one that works, check one out for me. I have one that a student restored in my office. So when they say take the resistance measurements in your lab assignment, you have to use the analog meter. If you try to take this measurement with a digital multimeter, you're going to get inaccurate results. What's that? Yeah, but the biggest thing is with a digital multimeter, it just doesn't give you an accurate read. Digital multimeters have a feature built into them that's called diode test. And when you use the diode test feature on a digital multimeter, instead of, basically, we're getting the cart before the horse. Let's take a step back. When you check it with an analog meter, what you're doing is you're checking the diode for the forward resistance and then the reverse resistance when you reverse the leads. In one direction, you're going to have a relatively low resistance. In the opposite direction, you're going to have a relatively high resistance. Does that make sense? So by checking that with an ohm meter and just looking for a low resistance one way and a high resistance one way, you just prove that that diode is functional. When you use the diode test feature of a digital multimeter, what's going to happen is you're putting a higher bias voltage across it, and that diode test feature is going to give you a voltage, not a resistance. A voltage, not a resistance. Ironically, when you forward bias the diode, does anybody want to take a guess what voltage it gives you? The voltage drop across it, the forward bias voltage. Yep, so when you use diode test feature and you put the black lead on the cathode, the red lead on the anode, you look at your digital multimeter, it should say something close to 0.6 or 0.7 volts. When you reverse the leads on a digital multimeter, then it should say OL, or out of limit. How would you, some of the best questions you ask me are questions that I'm going to turn around and ask you. How would you determine with a multimeter, DMM, whether it's silicon or germanium? What's that? Yeah, by the voltage. So simply by pulling out a digital multimeter, putting it in the diode test feature, you can not only test the diode, you can also identify whether it's silicon or germanium. So that's how you test it. Real simple process. Is there any way of testing what the impurities are? No. I have no way. The impurities, what dopants were used? No idea. I don't even know if the data sheet would show what. You're looking at the wrong data sheet. Yeah, it should identify whether it's silicon or germanium. Because if you're trying to find a replacement diode for a circuit, an adequate, suitable replacement, you need to know that. You need to make sure that you don't put a germanium where silicon was or silicon where germanium was, without doing some engineering. Okay, in summary, junction diodes are created by joining N-type and P-type materials together. Depletion region is the area near the junction. The charge at the junction creates a voltage called a barrier voltage. Current flows through a diode only when the external voltage is greater than the barrier voltage. A diode that's forward biased conducts current. A diode that reverse biased conducts only a small leakage current. That's why it's called a diode. That's why it was invented, to do this. Allow current to only flow one way. That makes a diode a one-directional device. The manufacturer specifies a diode's maximum forward current and reverse voltage. This is done on the data sheet. Schematic symbol for a diode. A for anode, an arrow, cathode. Well, that's the other side. You want to put a negative on the cathode, a positive on the anode, that's going to forward bias it. If you do the opposite, it's going to reverse bias it. The cathode is the N material, the anode is the P material. There's three ways of constructing diodes: growth, alloyed, and diffused. Diffused method is the most commonly used today because it really gives us the best control over the process of manufacturing the diode. Not necessarily. Some of that diffusion equipment is pretty expensive, but for the size of components now, it gives them a lot more control. A diode is testing by comparing the forward to reverse resistance with an ohm meter. When I say ohm meter, I'm talking about kicking it old school, an analog instrument. So when you're doing your labs, make sure if they say measure the resistance, you're going to have to use an ohm meter. I recommend you do both. Okay? It's easy to set up a digital multimeter and measure the forward reverse test using a DMM. But when you're measuring resistance, you're going to have to kick it old school and use an analog meter. Forward biased diode is going to have low resistance. Reverse biased is going to have high resistance. Anybody have any questions for me on anything associated with the diode? PN junction diode. All right, very good. Let's go ahead and take about a 20-minute break. And when we come back, chapter 21. But again, it is still arsenic, so in a manufacturing facility, a fab, right, this stuff is hazardous materials.